My name is Nathan Sturtevant, and in this video I'm going to be telling you about some work that I did together with my research associate, Ehsan Futuhi, on looking at depth-first search algorithms combined with neural heuristics. And so we have this long title for this paper, but really this notion of batching neural heuristic lookups and depth-first search is the core idea that we're going to present in this paper. Now, the context of this work is in shortest path algorithms. And the idea of a shortest path algorithm is I've got a start state, a goal state, and I'm trying to find a path in between them. And the key thing is that I have a heuristic that's going to guide my way. And so the example down below is a problem where we have a heuristic that provides a reasonably strong heuristic to guide the search as we're trying to find this path. In particular, in this paper, we're thinking about heuristics that are neural heuristics. That is, they come from a neural network. There's a number of different examples of ways that people have done this in the past. This paper doesn't contribute to how to build neural heuristics, but we're going to assume that we have them available. They've been learned, and we can use them to guide our search. This isn't the only approach, just in terms of context. You can also be looking at policies, or you could try to use your GPU, for instance, directly to run your algorithm. But here we're looking particularly at neural heuristics. And there's two approaches that have been used with neural heuristics. One of them is classification. And if I have a small number of values, I can build a classifier to get my heuristic values out, which is nice. It gives us discrete values. The other approach would be to use regression, which will give us a more continuous range of heuristic values. And this impacts how we want to use these heuristics. In particular, if we want to combine them together with search, when we are using neural networks, we need to batch our operations. We need to take many states and compute the heuristic at the same time if I want to do this efficiently. Because this is sort of the core foundation of how our GPUs work for doing this parallel inference. There are algorithms that have been designed for best first search, like batch weighted A star or batch A star. And in this paper, we're really just asking this question: how do we batch depth first search when we need to get our heuristics from a neural network? So there's two really common depth first search algorithms that are used in heuristic search. The classic one is IDA star, which works when you have a nice exponentially growing tree, and usually this requires unit cost edges. And then this algorithm runs in time, which is b to the d in the best case. Budgeted tree search is an improved version of IDA star, a more recent algorithm, so not quite as well known, but it can handle quite a different variety of costs. In the case where we have well-behaved edges and well-behaved costs, then it performs the same as IDA star. But in the worst case, the overhead is only this log C star overhead, where C star is the optimal solution cost. And so in practice, this can be a better algorithm. Now, the core thing that exists in both of these algorithms is something called a cost-bounded depth-first search. And I'm going to illustrate what this is by looking at this tree, which is on the right of the slide here. And well, let's just run. This is what actually happens. So this is a tree with non-unit costs, and IDA star performs very poorly on this. Instead of having these iterations grow exponentially, they're growing linearly. But actually, the point here is not the poor performance of IDA star in this particular problem, but it's this notion that we have these states here which are highlighted in blue. And those are all the states that have costs that's less than a particular cost bound. And what IDA star does, and budgeted tree search, is one of their core operations is to do the depth first search, which is the black states that's going across in the animation, a depth first search through the states of a given cost bound. And so this tree is particularly small, but the trees could be quite large. And if we can effectively batch our heuristic lookups in the cost-bounded depth-first search, then we're going to be able to take both IDA star and budgeted tree search and run them efficiently in practice. So in order to understand how we do this in the paper, we first are going to look at how we do parallelization of our CPU. And this is an algorithm that dates back to 1994 called AIDA star. And the idea of this algorithm is that we're going to do some initial search, which we've highlighted the states in that search in blue. And what we're going to do is we're going to notice that at the leaves of this search, at these leaves, we have these nodes that can be searched entirely in parallel. there's no communication that's needed in a particular depth-bounded, cost-bounded depth first search between each of the nodes here. So we're going to take these nodes, we put them into a work queue, and then we search them independently. And this will give us nice CPU parallelization. So we just, all of those go into a queue, and then we run the trees below them independently. Now, if we want to go and run this not just on the CPU, but we also want to use a GPU to get the heuristics, one of the things we need to know is that every time we come to a state, we have to look up that state's heuristic. And so that's a really expensive operation that we want to be able to batch to make it more efficient. And so the idea here is we're going to take this shared work queue, which is on the left-hand side, and in AIDA star, we take one state at a time and we send them to our different CPUs. Here we're going to use two representative CPUs, but what we're going to do is instead of taking a single state out of this, we're going to take batches of states onto my CPUs, so groups of states. And all of these states are going to represent search trees that are, that are rooted at some node from this initial search. And what's going to happen is that we're going to start searching through these trees. So we send them both to the first and second CPU. We start searching through these trees, and what we're going to do is we're going to come to the first one. We're going to expand a state. We need to look up the heuristics of the successors, which we can't. We need to do that on the GPU. So then we're going to say, well, we can't make any more progress, and then we'll go to the next one and the next one. Our second CPU at the same time is going to be trying to go through and make progress on each of these pieces of work, and it's going to be successively be blocked by the need to look up the heuristic values. So what we're going to do then is send those heuristic values across to our to a shared queue, and when that queue gets filled up, we have another thread, which is taking the job of now taking these, moving them to the GPU, and then calculating the values there, the heuristic values on the GPU in parallel in one single batch. And those states can then be sent back to our CPUs, which allows each of these searches to be unblocked and continue. And we're just going to loop through this process of getting work, sending it to these batches, sending the batches to the GPU, and then going back to RAM. The exact details of how this works are in the paper, so I'll have to refer you there to see some more details of how we implement this. But in terms of performance, what we can see here is that we have two sample domains. On Rubik's Cube, if we have a batch size of 1, in this particular example, we couldn't solve any of the problems in the time limit. Sorry, we couldn't solve all the problems. The sliding tile puzzle, we get particular performance here. But as we increase the batch size, then on Rubik's Cube, we're significantly reducing the time. We also are in sliding tile puzzle up to a particular limit, and the amount of work we have to do stays about the same here. The exact details of why they change by small amounts, you'd have to look at the paper to see some more information about that. This is a non-unit cost domain here. So this is an example where IDA star actually doesn't work, but budgeted tree search does. And what we see here on two different sizes of Rubik's Cube, that using these larger and larger batches results in significant speed up of our searches. So this should give you some evidence that we are able to take the batching that we need for our neural heuristics, and we can use IDA star or budgeted tree search, and we can do that batching to make the search efficient. And so this is going to expand the types of algorithms that we can use with neural heuristics. And of course, it enables us now to look at bigger and bigger neural heuristics and have some algorithms that we can use in order to solve problems with those heuristics. So thank you for listening. Again, I refer you to the paper if you have additional questions. And I want to acknowledge funding from Amy and CFAR, and also to my colleagues who contributed to this work in various ways. So thank you, and please look at the QR code to find the paper for more details.